Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you look for videos explaining topics in college mathematics courses, please consider subscribing because you are in the right spot. Let's go ahead and get into the current video. I want to talk about the local quadratic approximation to a function in two variables. Now, in your Calc 2 course, near the end, you talked about how to find a quadratic approximation to a function of one variable using what's called a Taylor polynomial. And so what I want to do is let me remind you of both what that looked like geometrically and then using a formula for that. So let's say I have the following graph. And let's say this is, again, y is equal to f of x. So this is the graph of a function of a single variable. And let's say I wanted to find a quadratic approximation at, so I'll just conveniently pick, say, a point like this. So what is the quadratic approximation at the point at the top of that? And let's say this refers to or corresponds to the point when x is equal to a. Well, a quadratic approximation would give a graph of a quadratic function, which, let's say, I'm just trying to figure out what color to use here. I guess this one will work. Let's say the graph looks something like this. All right, and so I get a parabola at that point. Now, of course, not only is it going to match at that point, like think about a tangent line. Of course, it matches at the point of tangency, but as I move away from that, the quadratic is going to match that curve better than a straight line would. So even if I get a straight line approximation, so the tangent line, the quadratic approximation probably matches the graph better a little bit farther out. So it matches it better as I get away from the point of, say, tangency there. And Taylor polynomials or Taylor series, we could add more terms to that, but we're just going to focus on a quadratic approximation. Now, if you remember, the formula for a quadratic approximation, so the Taylor polynomial of order 2, is given by the following. Y is equal to the function value f of a plus the first derivative at a times x minus a plus the second derivative at a over 2. It's 2 factorial, which of course is equal to 2, but usually we write it as 2 factorial just as a reminder that the rest of the denominators are factorials, and then x minus a squared. Notice that the coefficients are all constants, and then if I was to multiply this all out, I would have a power of x squared, at least at most x squared. Therefore, this would be, assuming the second derivative of a is not a constant or not 0, this would be a quadratic function. Well, what I want to do is let's take a multivariable function and let's provide a quadratic approximation to that. What would be the analogous equation for this? Well, function value, that's going to be just a function value, not a big deal. First derivative and the second derivative, and even this x minus, well, not the x minus a so much, but the x minus a squared, we have to kind of come up with some analogies between those concepts. Now, if you watch the previous videos on the total derivative of a function and the Hessian of a function, that's going to come into play here. Let's go ahead and take a look. Here would be the quadratic approximation of a function of two variables at a specific point. So f of xy is going to be approximately equal to, again, this is at a point AB, so at a point AB, so at the point AB, is approximately equal to the function value, f of AB, plus, I'm going to take the gradient of that function, okay? Remember, the gradient of the function is the vector that has all of the partial derivatives. And when I talked about the total derivative, that does have, it's basically a matrix that has all possible partial derivatives. So that's kind of the gradient plays the role of the total derivative. and it's going to be the gradient evaluated at that point. And then I'm going to take the dot product of that with, I'll write this as a column vector, x minus a, y minus b. This plays the role of this part right here. I'll kind of match these up after I kind of finish this. Plus, I'm going to have a column vector, x minus a, y minus b. And then I'm going to take the dot product with the product of the Hessian of the function evaluated at p multiplied by x minus a, y minus b. And then, oh, and then this actually, I forgot one thing. Just going to scoot that over. There is a coefficient of a half. X minus a, y minus b, dot product with this. All right, let's now go ahead and match this up. What I have is, of course, let me see what colors might work well here. I guess maybe red might stand out the most. Maybe, who knows? The function values, those, of course, correspond. And then the first derivative is going to correspond to the gradient of the function. The product of the variable is going to correspond to this vector here. Of course, this has a 1/2, this has a 1/2. The second derivative corresponds to the Hessian of the function. And the x minus a squared, well, I have this variable, think of the factor of x minus a just as appearing twice. Well, it appears, of course, here, and it appears here, which is going to give me possibly a squared variables, or x times y, something like that, which is a second order term. The way I multiply this here is this is a matrix times a vector, which is going to give me a vector, and then I'm going to compute this vector times this vector through the dot product. All right. And that right there is going to provide me with a local quadratic approximation to a multivariable function. Let's go ahead and do an example. Okay, so just so I can kind of refer to things, I rewrote that so it's at the top of the screen. Now let's take a look at a function of two variables. Let's say I give you f of xy is equal to y cosine x plus x sine y, and we are going to look at the point at the origin. So let's find a quadratic approximation to this function at this particular point using the above formula. All right, well, we have to compute a variety of things. First and foremost, we need the function value. F of 0, 0, so f at the point P, f of 0, 0, 0, of course, is 0. And then I'm going to need the gradient of the function. So the gradient of the function, and I'm going to write it as a column vector, just because when we do, say, the Hessian, we might want to have it as a column vector like we did in the previous video. So the gradient of this function, so partial with respect to x, would be negative y sine x plus sine y. The partial with respect to y would be cosine x plus x cosine y. And then what I need to do is evaluate the gradient at the point. The gradient of f at the point P is going to be the vector. If I plug in 0 here, that's 0. If I plug in 0 here, that's 1. So 0, 1. Right? That's that component. Then the next thing that I need is to compute the Hessian of the function. Well, remember that the Hessian, we build that from taking the total derivative of the gradient, and that's going to give me a matrix. take the total derivative of the gradient. Well, let's, rather than thinking this as a gradient, let's think of it as a function of from two components to two components. So this is going to be my first component function. This is my second component function. And what I do is I take the gradient of this, which would be negative y cosine x. And oh yeah, with respect to x, it would be negative y cosine x. And then derivative with respect to y would be negative sine x plus cosine y. And then here, the gradient of this expression would be negative sine x plus cosine y. And then with respect to y, I would have negative x sine y. Therefore, the Hessian at the point P would be, well, if I plug in 0, 0, that's going to give me a 1 here and a 1 here. So I get 0, 1, 1, 0. All right, so that's all the different components that I need to go ahead and pop into that formula. So again, let me sort of section this off, because I'd like to keep everything up here ideally. And let's go ahead and plug things in. All right, the function that we started with is approximately equal to function value, which was 0, plus the gradient at P, which was the vector 0, 1. So I'll write it this way, 0, 1, dot product with, actually let's write it as a column vector. Try to be as efficient as possible with the space here. So I'm going to take 0, 1, and then I'll dot product that with, so x minus a. Well, remember, the point P is 0, 0. So a is 0, b is 0. That means this vector would be xy plus 1/2 times the vector xy times the matrix of the Hessian, which was 0, 1, 1, 0, multiplied by, sometimes I interchange parentheses and brackets, it really doesn't matter, x minus 0, y minus 0, which should be xy. All right, so let's go ahead and compute this. 0 plus, I'll drop that off. The dot product here, 0 times x plus 1 times y would be y, plus 1/2 times the vector xy. And this is going to be a dot product times, well, when I multiply this matrix by this vector, I'm going to get a vector. So 0, 1 dot product with xy is y. And then 1, 0 times xy would be x. Then this would be equal to, I guess this would technically be strictly equal to here now, y plus 1/2. Dot product here would be xy plus yx, which is another xy. So that's 2xy times 1/2, which would be xy. So I get y plus xy. So the local quadratic approximation to this function at the origin is y plus xy. Why don't I see an x squared or a y squared term? Well, x times y, the product of those two variables, is a second order term, even though I don't have a squared there because they're different variables. That does play the role of a squared term, and again, gives a quadratic approximation. Thank you for watching, and please consider subscribing. And one other video, I will do at least one more application of the Hessian of a function. But again, thank you for watching. Please consider subscribing.